Welcome back, my dear students, on a new lecture on functional analysis. So, in the previous lecture, we have discussed about the concept Hilbert adjoint operator in general. So, in this lecture, we will discuss some elementary properties of the Hilbert adjoint operator. So, before we getting into the properties, we need some results to establish those properties. So, the first result or the essential result which is needed to establish the properties of Hilbert adjoint operator can be quoted as a lemma. So, the lemma states that let x and y be inner product spaces and q from x to y a bounded linear operator, then first argument is q is equal to 0 if and only if inner product qxy is equal to 0 for all x element of x and y element of y. That is, if q is equal to 0, then inner product qxy should be equal to 0 for all x element of x and for all y element of y. And the second argument is if inner product qxy is equal to 0 for all x element of x and y element of y, then the operator q should be identically 0. So this is a necessary and sufficient condition for a bounded linear operator to be a zero operator. And in the case of a complex inner product space, if Q is from X to X, where X is a complex inner product space, and inner product Qx X is equal to 0 for all X element of X, then Q is equal to 0. For in the case of a complex inner product space, if Qx X is equal to 0 for all X, then Q can be identically called as 0. So this is the particular case when X is a complex inner product space. This cannot be stated in the case of real spaces. There are spaces in which inner product qx x is equal to 0 for all x, but q is not identically 0. But this is true for complex spaces. So these are the two results. So we have to prove this result. First we have to prove that q is equal to 0, then inner product qxy is equal to 0. So let us move on to the proof. So part A, assume that q from x to y is a bounded linear operator and q is equal to 0. Q is equal to 0 implies qx is equal to 0 for all x. Then inner product qxy should be equal to inner product 0y. It should be equal to 0 for all y. So when q is equal to 0, we can say that inner product qxy is equal to 0 for all x and for all y. Now assume that inner product qxy is equal to 0 for all x element of x and y element of y. Then by previous lemma, which states that inner product xy is equal to 0 for all y implies x is equal to 0. We have already established this lemma, 3.8.2. Please quote those lemma. So here inner product qxy is equal to 0 for all y element of y, which trivially implies that qx is equal to 0. Here this is true for all x. When qx is equal to 0 for all x, then we can say that q is essentially a 0 operator. From this, we can write qx is equal to 0 because we have a lemma which says that inner product xy is equal to 0 for all y implies x is equal to 0. Here, inner product qxy is equal to 0 for all y implies using this lemma qx is equal to 0. Now this equality is true for all x. Then qx is equal to 0 for all x, which is identically meaning that q is equal to 0. So that is when q is equal to 0, inner product qxy is equal to 0, and if qxy is equal to 0 inner product for all x element of x and y element of y, then q is identically 0. Now we are moving on to the second part. In the second part, we have to assume that x is complex and inner product qxx is equal to 0 for all x element of x. Now consider a v. V is of the form some alpha x plus y, where x comma y element of x and alpha is complex. Then using this result, then alpha x plus y is again element of x, which can be called as, so alpha x plus y, which is v, is an element of x. Then for all element of x, we have qx x is equal to 0. So using the argument, we can say that inner product qv v is equal to 0. Now replace v by alpha x plus y. This implies inner product q of alpha x plus y comma alpha x plus y is equal to 0. Now this can be written as, since q is a linear operator, this is alpha times qx plus qy comma alpha x plus y. Now this can be splitted as inner product alpha qx comma alpha x plus inner product alpha qx comma alpha y. Here it is y. Now plus inner product qy comma alpha x plus inner product qy comma y. Now we can return as such using the basic properties of inner product. Now from this implies, from this part we can take alpha outside, from this we can take alpha bar outside. Now this is implies this is alpha times alpha bar inner product qx x plus alpha times inner product qxy plus we can take alpha bar outside, alpha bar times inner product qyx plus this is qy y. Now this implies this is modulus of alpha square. Alpha times alpha bar is modulus of alpha square, given that alpha is complex. Inner product qx plus alpha times inner product qxy plus alpha bar times inner product qyx plus qy inner product. This should be equal to 0 by our assumption that inner product qvv is equal to 0, where v is taken to be alpha x plus y, where alpha x plus y is an element of capital X. Now since x is an element of capital X by our assumption, y is an element of capital X, so which implies inner product qxx is equal to 0 and inner product qyy is equal to 0. Okay. Now so we can substitute that in this expression, so we get the answer as alpha times inner product qxy plus alpha bar times inner product qyx is equal to 0. So this is equation number 1. Now since alpha is complex and alpha is chosen to be arbitrary, we can substitute any values for alpha. Okay. So choose alpha is equal to 1. So when alpha is equal to 1, this expression becomes inner product qxy. When alpha is equal to 1, alpha bar is also 1 because alpha is real. For a real number, a, a number and its conjugate are actually same. So inner product qyx should be equal to 0. So this is expression A. Okay. Now substitute, take alpha as I. So this implies I times qxy, alpha bar is minus I times qyx should be equal to 0. Now we can take I outside, that is I times inner product qxy minus inner product qyx should be equal to 0. Now I is not equal to 0. So the product is should be equal to 0 means the second part should be equal to 0. So this implies inner product qxy minus inner product qyx should be equal to 0. This, consider this as equation number B. Now adding equation A plus equation B, we can cancel inner product qyx. This should be equal to 2 times inner product qxy should be equal to 0, which implies inner product qxy should be equal to 0. Now this is true for all x element of capital X and for all y element of capital X, since we have chosen x and y to be arbitrary. So inner product qxy should be equal to 0 for all y element of capital X. Then again applying theorem 3.8.2 lemma, inner product xy should be equal to 0 for all y implies x is equal to 0. So inner product qxy is equal to 0 for all y implies qx is equal to 0 for all x. This is true for all x and all y, which implies q is identically equal to 0, which is what we need to establish. So in the case of a complex space, inner product qx x is equal to 0 implies that q is equal to 0. So this is in the case of a complex space. So we have established the necessary and sufficient condition for an operator to be 0 operator in the case of two arbitrary inner product spaces, and in the case of particular complex space we have established one particular case of existence of 0 operator. Now I have already told you for inner product qx x is equal to 0 implies q is equal to 0. The second part of the previous lemma is true whenever x is a complex space. So whenever x is real, it may not be true. So we give a particular example for that, which can be quoted as a remark. So we will give you a particular example in the case of real space in which inner product qx x is equal to 0 for all x when q is not equal to 0. Consider our space. Consider x is equal to r square and q is the rotation by a degree pi by 2. So for every element in r square, q transforms an xy or rotates an element xy by a degree pi by 2. So qx, if we consider an x element of r cube, r square, Qx is actually orthogonal to x because Qx is being rotated by a degree of pi by 2. Okay, so if you consider this as x, then in order to obtain Qx, we have to rotate this to a degree of pi by 2. So this is Qx. If this is x, corresponding angles will be pi by 2. Then Q of x is actually orthogonal to x. When Q of x is orthogonal to x, inner product Qx x should always be equal to 0. So this is true for all x in this case. But since Q is the rotation by a degree of pi by 2, Q cannot be equal to 0. So this is a particular example in which inner product Qx is equal to 0 for all x, but Q is not in general 0. So for x to be complex is an essential argument in the previous lemma. When x is not complex, the result may not be true. This is a particular counterexample for that. Thank you.